Double coil syndrome is a common issue encountered in PLC programming, where the same output is controlled from multiple locations within the program. This overlapping control can result in unpredictable behavior, as the output state may change unexpectedly depending on which part of the code executes last. Such situations make it difficult to trace the source of errors, complicating the debugging process. Understanding and identifying double coil syndrome is crucial for maintaining reliable and manageable automation systems. Double coil syndrome occurs in ladder logic when multiple rungs attempt to control the same output coil. For example, two separate rungs might each contain an instruction to energize the same motor output, depending on different conditions. This can lead to unpredictable behavior, as the output state may change unexpectedly based on which rung is evaluated last during the scan cycle. Visual diagrams often show overlapping coils, highlighting how conflicting instructions can make troubleshooting difficult. Recognizing and avoiding double coil syndrome is essential for reliable and maintainable control system design. Double coil syndrome presents significant challenges in electrical systems, primarily due to the last scan wins effect. This phenomenon occurs when two coils attempt to control the same output, leading to unpredictable output states depending on which coil is processed last during a scan cycle. Such unpredictability can result in erratic system behavior, making troubleshooting and maintenance far more complex. Additionally, identifying the root cause of issues becomes difficult, as the output may change unexpectedly without clear indication. These factors contribute to increased downtime and maintenance costs, highlighting why double coil syndrome should be avoided in system design. Consider a scenario where two different rungs in a ladder logic program both assign values to the same output. If the first rung sets the output to on and a later rung sets it to off, the final state of the output depends entirely on the order in which the rungs are scanned. This can lead to ambiguous or unintended results, especially if the programmer is unaware of these conflicting assignments. Such situations highlight the critical importance of understanding and managing scan order to ensure predictable and reliable output behavior in automation systems. To prevent double coil syndrome, several best practice solutions can be applied. One effective approach is the single coil principle, which ensures that only one output is assigned to each coil within a program. Using internal flags can help manage intermediate states and reduce the risk of conflicting outputs. Additionally, implementing state machines provides clear and structured control over output signals, making it easier to track and manage transitions. These methods collectively contribute to safer and more reliable automation system design. Detecting and preventing double coil syndrome involves a combination of technical and procedural strategies. Software warnings can automatically flag potential issues during development, alerting programmers to problematic patterns. Cross-referencing code helps ensure that overlapping or redundant logic is identified and addressed early. Adhering to established coding standards promotes consistency and reduces the risk of errors. Regular code reviews further enhance detection, as multiple perspectives can spot subtle problems that might otherwise go unnoticed. In certain specialized applications, assigning multiple coils to the same output can be acceptable. This approach is often seen in intentional set or reset logic, where distinct coils are used to explicitly control the state of an output. Another example includes carefully designed mode overrides, allowing different operating modes to take precedence under specific conditions. While these configurations can offer enhanced flexibility, they require meticulous planning to avoid unintended conflicts. Proper documentation and thorough testing are essential to ensure reliable operation in these scenarios. Modern programmable logic controllers, or PLCs, are equipped with advanced features that enhance output control in industrial automation. Among these features Arbitration logic plays a crucial role by resolving conflicts when multiple instructions attempt to control the same output. Additionally, priority-based instructions allow the system to determine which commands take precedence, ensuring that critical operations are executed reliably. These capabilities contribute to safer and more efficient process management, reducing the risk of errors and downtime. As a result, PLCs provide robust solutions for complex automation tasks in various industries. Consolidating control signals and assigning each physical output from a single location in the program is essential for maintaining clarity and reliability in system design. This approach reduces the risk of conflicting commands and makes troubleshooting much more straightforward. By centralizing control, developers can easily track changes and ensure consistent behavior across all outputs. Ultimately, this practice leads to more robust and maintainable code, supporting long-term system stability.